In 1872, the British astronomer Richard Proctor was nominated for the Gold Medal of the Royal Astronomical Society. Proctor was at the time secretary of the Society and a prolific contributor to the monthly notices of the Royal Astronomical Society. But in an unprecedented move, the nomination was subsequently withdrawn, and it was decided that no medal would be awarded for that year. Proctor suspected that George Airy, the current Astronomer Royal, was behind the strange turn of events. Airy was a prime suspect because Proctor had earlier criticized the Astronomer Royal's plans for studying the upcoming transit of Venus in 1874. Never one to back down from controversy, the pugnacious Proctor went on the attack. He renewed his criticisms of Airy's plans, and in the process made negative references to the British Admiralty, under whose auspices Greenwich operated. This angered some members of the Royal Astronomical Society. In his role as editor of the monthly notices of the Royal Astronomical Society, Proctor published a supplement to the June 1873 edition that focused on the transit enterprise and repeated his criticisms of Airy and the Admiralty. Airy responded by condemning Proctor, and the RIS Council viewed Proctor's actions as a misuse of his office. Proctor resigned as secretary and editor, and in May 1874, he read a semi-apology to the Society. After that, Proctor took no further active part in the Society. But later, when the disappointing results of the British transit enterprise of 1874 were published, there was widespread agreement that Proctor's criticism of Airy and the Admiralty had been justified. Lying behind this extraordinary chain of events was a fundamental disagreement over how the Victorian astronomical community should study the heavens. For Proctor, Airy's Greenwich Observatory had adopted a hierarchical military model of doing science that made blunders, such as those concerning the 1874 transit of Venus, inevitable. Richard Anthony Proctor was the youngest of 4 children of William Proctor, a wealthy lawyer. In 1856, he entered St. John's College, Cambridge. In accordance with his mother's wishes, Proctor intended to enter the church and read theology and mathematics. After graduating in 1860, with a disappointing academic record, he decided against the ministry and he began to study law. He became fascinated by astronomy soon after leaving Cambridge, and he decided to train himself in the subject so he could teach his eldest son. When his son died in 1863, Proctor's initial reason for learning astronomy was gone, and he became distraught over his son's death. His health began to fail. His doctor advised him to immerse himself in some form of work that would occupy him for at least a year, and Proctor chose the study of astronomy. By 1865, he had written a monograph titled Saturn and Its System. Though the book was a commercial failure, it was a critical success, and it led to his election in 1866 as a Fellow of the Royal Astronomical Society. In 1866, a failed investment ruined him financially, and it forced him to make a living as a science journalist and writer. Proctor slowly established his credentials as an astronomer who could write for the public. None of his early books sold particularly well at first. He finally produced a commercially successful work, Half Hours in the Telescope, published in 1868, and the book eventually passed through 20 editions. But Proctor's breakthrough work was his Other Worlds Than Ours, published in 1870, in which he focused for the first time in his writing on the theme of life on other planets. After 1870, Proctor had little difficulty finding a publisher or journal editor who would accept his work. Astonishingly prolific, Proctor wrote over 60 books in his career, perhaps the most of any 19th century popularizer of science, not to mention the countless articles. Proctor's ability to churn out books and journal articles at a breathtaking speed attracted criticism from some who believed that it compromised the quality of his work. So take, for example, a review of Proctor's books in 1875 in the New York Times, which declared, somewhat tongue-in-cheek, quote, This is getting serious. Mr. Proctor's books come so fast that no moderate-sized library will be able to hold them in the course of another year or two. Quote. But during the early 70s, Proctor was still conceiving of himself as a practitioner of astronomy and not only a popularizer. He attempted to bolster his scientific credentials in the late 60s and early 70s by submitting articles to the monthly notices of the Royal Astronomical Society and other scientific journals. His decision to criticize Airy's plans for the 1874 transit of Venus may have been part of a strategy to boost his scientific reputation. Proctor first examined the plans for the 1874 transit in March of 1869, when he reported in a short monthly notices of the Royal Astronomical Society article that he had found some inaccuracies when he applied geometrical tests to the maps in Airy's previously published articles. 3 months later, Proctor presented his own maps of the upcoming transit. He then called into question some of Airy's plans for the observation stations. He argued that Airy had not adopted the optimal station arrangement for observing the transit. In all, Proctor published 6 articles on the topic of Airy's plans in the 1869 volume of the monthly notices. At this point, however, Airy did not believe it necessary to reply publicly to Proctor, and nothing came of Proctor's criticisms in 1869 or for several years thereafter. But early in 1873, as the transit drew nearer, the London press began to take an interest in the issue, and its attention was drawn, likely by Proctor himself, to his earlier disagreement with Airy. On February 8, 1873, the London Spectator warned that Britain could, quote, suffer serious discredit from the manner in which the phenomenon is to be observed, end of quote. Taking Proctor's side, the Spectator made the success of the transit project a matter of national honor. 5 days later, The Times published a lengthy and technically detailed article that was quite similar in tone. The newspaper articles roused the Admiralty's interest in Proctor's claims, as both of them referred to the shame that would be faced by the Admiralty if the failure of the expeditions were due to problems that could have been corrected. The day after the Times article appeared, the secretary of the Admiralty wrote to Airy asking, quote, whether the articles in question are founded on fact. At this point in time, George Airy was the most prominent public science service in Britain, and the Royal Greenwich Observatory was at the center of the Victorian network of military imperial science. Airy had been Astronomer Royal from 1835, and his effect on the institution had been enormous. During his long career, he had retained and reinforced Greenwich's devotion to positional astronomy. This involved mapping the sky by observing the transits of stars and other celestial objects across the Greenwich meridian. Airy was known for enforcing a strict discipline in his observers in order to eliminate all personal bias and obtain precision measurements. Precision measurement was crucial to a nation that controlled roughly half of the world's maritime commerce. Although there were cries throughout the 19th century that the British state did not fund science adequately, significant resources were provided for a number of ambitious scientific projects run by the government. The Global Geomagnetic Research Program, spearheaded by Henry Sabine, an officer of the Royal Artillery, is just one example of how big science was supported by the British state. Other examples would be the trigonometrical surveys of Great Britain, begun in the first half of the 19th century, the Geological Survey of Great Britain, begun in 1835, and the pioneering survey of the HMS Challenger from 1872 to 1876. The significant funding provided for the Transit of Venus enterprise was thus another case in point. Due to Airy's position as a prominent public science servant, and to the tradition of state funding of big science projects of national interest, there is no real concern within the government about Airy's ability to manage the transit project. However, Airy replied to Proctor in the next issue of Monthly Notices and claimed that there was nothing that Proctor had raised that he hadn't already thought of. He argued that Proctor's recommendations on the placement of observation stations were not practical. When the subject came up in Parliament in March 1873, Airy's reply to Proctor in the Monthly Notices was read verbatim by the First Lord of the Admiralty. In the next few months, Proctor published 8 more articles on the subject of the transit in the Monthly Notices, reiterating his arguments. But he also began to write articles on the topic for periodicals read by the general public. He wanted the public, as well as scientific practitioners, on his side in his fight with Airy and the Admiralty. In March and June 1873, 2 of his articles on the transit of Venus were published in a journal titled Fraser's Magazine, which was a literary miscellany with an emphasis on politics, religion, and social issues. If we examine Proctor's articles in some detail, the scientific dimensions of the quarrel between Proctor and Airy will become clear. Proctor pointed out that the transit of Venus was important in astronomy because it, quote, affords the most satisfactory means of determining the distance of the sun. In other words, the dimensions of the solar system itself, end of quote. Measuring the solar system allowed astronomers to measure, quote, the vast spaces which separate us from the fixed stars, end of quote. So in other words, all accurate astronomical measurement, according to Proctor, rested primarily on having the correct value for the distance between the Earth and the sun. So the observations made in 1874 were, as Proctor declared, directly related to, quote, the fundamental problem of astronomy as far as astronomy relates to the determination of the distances and magnitude of the celestial bodies, end of quote. Since the transits of Venus were short and rare, that phrase is Proctor's phrase, and since they offered the best opportunity for calculating the distance from the Earth to the sun, it was crucial, Proctor argued, for Airy's plans to be well thought out. But Proctor insisted that Airy was using the wrong method to study the transit, and as a result, the entire project had been compromised. Airy believed that taking into account the circumstances in 1874, the Delisle method should be used. Proctor had concluded in 1869 that the Halley method was far superior for the 1874 transit, though he argued that both methods should be employed. That way, if the results corresponded closely, if you use the 2 different methods and you get the same results, then astronomers could have more confidence in the results. What were the Delisle and Halley methods? Proctor discussed their differences in his Fraser Magazine articles and in almost every other article that Proctor wrote. Edmund Halley, Astronomer Royal at Greenwich, devised what came to be known as the Halley method in 1716. His method depended on having observers measure the duration of the transit with as much precision as possible. But a station well placed for observing the beginning of the transit might be ill-placed for observing the end, and vice versa. So, Halley's method required more than one observing station, and it worked best if the stations were located fairly far apart. During the 1750s, Joseph Nicholas Delisle, a court astronomer in St. Petersburg, revived and revised Halley's method. Delisle's method only required observations to be taken at either the beginning or the end of the transit, not both. But it was hampered by a problem that did not come up in Halley's method. The 2 observers employing Halley's method only have to consider how long the passage of Venus over the sun's face lasts, and did not need to know the exact time at which the transit begins and ends. But for Delisle's method, 2 observers must know the exact time that the transit begins, even though they are 1,000 miles apart or more. Proctor believed that the instruments needed to measure time exactly enough were not yet in existence to ensure that observations were undertaken simultaneously. Proctor therefore favored Halley's method because it was, quote, the simpler of the 2, end of quote. Quote, for when an observer has estimated a duration end of the matter, he has that duration recorded and the comparison can be made with the other duration in the most direct way, end of quote. However, Airy's preference for the Delisle method had determined where the British observing stations were to be located, whereas the southern stations were suitable for using both methods, the northern stations, Proctor said, were not. Around the time of the publication of the second article in Fraser's magazine, that is June 1873, Proctor's attacks on Airy and the Admiralty had led to a backlash against Proctor by members of the Royal Astronomical Society, which led to his eventual leaving the society and resigning as editor of the journal. His influence on the transit enterprise declined thereafter. British preparations for the transit continued as Airy virtually ignored Proctor's objections. Airy planned to use 4 different methods of recording data: eye observations of the time at which the transit began or ended, photographic records of the time at which the transit began or ended, live measurements of the distance between the center of the Sun and the center of Venus during the transit, and measurement after the fact of the photographs that were taken. The observers who were selected to go on British expeditions were trained at Greenwich for 2 to 3 months so that they would become reliable. So this is all part of Airy's precision measurement program. The training covered the handling of instruments and the assembling of the prefabricated instrument cabins according to exact instructions. Airy also designed a model simulating the transit to train observers selected to go on the British expeditions. The first version was erected in October 1873 at Greenwich. Trainees viewed the model from a distance of 400 to 500 feet through a telescope. Though it had not been purposely built into it, the model produced what was called the black drop effect. This black drop had observed in the 1769 observations of the last transit of Venus. Observers were trained to become familiar with the phases of the black drop in order to minimize any differences in interpreting the beginning of the transit. So remember, the Delisle method, you have to determine the beginning at the exact time. But when the black drop occurs, it's sort of hard to know exactly when the beginning is. Is it when you first start seeing the drop form, or when there's a space of light in between, the outer rim of the sun and the silhouette of Venus? So the issue of when things begin and when they end was crucial for the Delisle method. The general assumption was that compared to the observations of the last transits in the 1760s, the observers of 1874 had more sophisticated telescopes and new technologies of modeling, photography, and steam travel, as well as a grasp of the central problems and more effective ways of finding their solution. 11 British stations were to be set up, centered in Egypt, Hawaii, Rodriguez, which is the island off the coast of Madagascar, New Zealand, and the Kerguelen Islands in southern Indian Ocean. As the expedition set out in the summer of 1874, confidence was high. The transit took place on December 8th and 9th of 1874, and for a few days, the transit of Venus was front-page news in every major European language newspaper and in many regions on the imperial periphery. Although there had been poor weather in New Zealand and in parts of Kerguelen, the observations were generally said to have been a success. But many of the British observers were surprised that no black drop effect was seen. The fact that the transit did not conform to the model confused some British observers and cast doubt on their results. As it turned out, Airy had problems with both the photographic data and the observations reports. Airy conceded that the photographic program had been a complete failure. Overall, no clear result as to the distance between the Earth and the Sun could be drawn. The first official report, published in July 1877, was disappointing to the astronomical community. Calculation of the distance to the Sun was not made more precise by the results of the transit expeditions. Airy, who had based his reputation on precision measurement in astronomy during a time when a new quantification wave spread throughout the scientific practice in general, found himself bogged down in a morass of imprecision. Proctor was only too happy to say, "I told you so." In an article on results of the British transit expeditions published in the late 1870s, he reminded his readers that Airy had selected the observing stations on the false assumption that the Delislean method was the only one available in 1874. As a result, Proctor argued, the information needed to use Halley's method, as a result, Proctor argued, the information needed to use Halley's method could only be obtained by combining British observations with those taken by American, German, and Russian astronomers who had stations in the proper northern locations. And how was one supposed to verify that their observations were accurate? Airy's approach had, quote, failed under the test thus applied to it, end of quote. For Proctor, Airy's failure pointed to a deeper problem with government astronomy. Still smarting from the condemnations of his fellow astronomers in 1873 in the Royal Astronomical Society for daring to criticize Airy and the Admiralty, Proctor drew an important lesson from the entire debacle. So here's Proctor's summary of what we're supposed to conclude after seeing this gigantic failure. Many seem to suppose that astronomical matters are in some sense like military or naval maneuvers, to be discussed effectively only by those who are under authority, having also soldiers under them. In other words, by government astronomers. It would be very unfortunate for science were this so, seeing that in that case, those chiefly responsible for the selection of methods and the supervision of operations would be perfectly free from all possibility of criticism. No one under their authority would be very likely to speak unfavorably of their plans. And no one possessing higher general authority would be likely to have any adequate knowledge of astronomy to form an opinion, either as to the efficiency of the arrangements adopted in any case or as to the significance of the results obtained. So for Proctor, the authoritarian, top-down nature of government science in Britain was inimical to an essential requirement for successful science, open criticism. Airy's subordinates within the ranks of official astronomy were required to maintain a judicious silence. They could not say anything to endanger their position. That left it to those outside the ranks of official astronomy, like Proctor, to voice their criticisms of government plans for big science projects. Not only were practitioners competent to express their views, they even had, quote, a duty of speaking, end of quote. Proctor's past actions, he was implying, were justified by a moral imperative. Proctor could not resist making a final point about the status of government astronomy. He acknowledged that the nation required a class of trained astronomers to carry out observations that were essential for the regulation of Britain's commerce. But these observations had, quote, scarcely any closer relation to the real living science of astronomy than land surveying has to such geology as Lisle taught, end of quote. What Airy and his subordinates did was more celestial surveying than astronomy. The severe disciplinary regime established at Greenwich, the factory mentality that dominated the observatory in order to ensure precision, were to Proctor merely signs of the unimaginative science practiced by Airy and his government colleagues. It was those astronomers outside the ranks of routine official astronomy who apprehended, quote, the true sublimity of astronomy as a science, end of quote. So Proctor used a controversy over the transit of Venus results to assign government astronomy a very low place within the British astronomical community. What happened to Airy and Proctor after the controversy was concluded? Airy retired in 1881 at the age of 81, wearied by the long-continued drag of the transit of Venus work, which went on and on and on. Though there was no official criticism of Airy for the failure of the transit enterprise, the disappointment over the results ended his 46-year career on a sour note. Proctor's reputation was enhanced by the final outcome of the debate with Airy. According to Otto Struve, a Russian astronomer, Proctor was among those considered as Airy's successor as Astronomer Royal. But after being condemned by the members of the Royal Astronomical Society for his attacks on Airy in 1873, Proctor had effectively withdrawn from professional science and had become a popularizer. Instead of pursuing a place in astronomy as a practitioner, he went on to establish himself as one of the most influential popularizers of astronomy in the 1870s and 1880s. In 1881, Proctor launched a new journal titled Knowledge, which was designed to challenge the journal Nature for control of the upscale science periodical market aimed at a popular audience. Despite Proctor's death in 1888, the journal survived well into the second decade of the 20th century, though it did not outlive its rival, Nature. While it lasted, Knowledge became more influential than Nature within the reading public. Knowledge not only allowed Proctor to maintain his position as premier popularizer of astronomy, it gave him a platform from which to continue his attack on government astronomers. When Airy retired in the early 1880s, Proctor now turned his guns on Norman Lockyer. Thank you.
One question. If there are any questions? Yes.
Were Proctor's complaints based on quantitative analysis or just argument?
Oh, no, he, in all of his articles, he presented quantitative analysis, he presented maps. No, he had...
So he could show the differential errors between the applications?
Well, he could show that the Delisle method wasn't the only method that could be used, and he could show that where the observation stations were placed would only allow for the Delisle method to be used. And so, his main argument was that not only is Halley's method superior because it's simpler, but also we should be using both methods if we want to have a check on each of the other methods. If we want to have a check on the Delisle method results, then we should use the Halley method. Well, they got results, but Proctor said they're flawed, and it was generally agreed that they were flawed because they didn't give any additional precision to previous results that had been obtained from previous transits. In fact, they gave even less accurate estimations. So that's why it was considered to be a complete failure. Given that they had all this supposedly advanced technology, they had the results of the earlier expeditions in the 18th century, and everyone had expected this was going to settle once and for all what the exact distance was between the Earth and the Sun.
What were the methods which the Americans and the Germans were using?
They were using mostly the Halley method, and Proctor really was enthusiastic about the American approach because they were using the approach most like his.
I think we have to finish here because the meeting is not on the I'm sorry. Professor Lightman will be available. You can definitely ask your questions to him.